So I'm Richard Asprey. I'm going to talk to you about Microsoft's Project Orleans, and we're going to build out an Internet of Things scenario. Has anyone here heard of Orleans before? One or two people? Anyone actually used Orleans? Nobody. Oh, we're going to learn something today. So I'm going to keep my slides to the bare minimum and try and spend more time in Visual Studio and try and be interactive and try and build some stuff. So fire questions as we go along, and don't be afraid to shout out. First of all, who am I and who are 210 Degrees? I'm an Azure MVP, and I've been working alongside guys in Microsoft for a while now. 210 Degrees, we kind of specialise in always being on the leading edge of what Microsoft are bringing out, and always trying to help other software businesses understand what these technologies are and to build software around them. So that used to be Bing Maps, it used to be the Pixel Sense Surface tables, which never really took off. And more recently, that's Windows Azure, and now things like Orleans and Windows RT. So you'll often find us around Europe helping other software businesses understand what these things are and understand how to build applications of the cloud, as Planky has just shown us. We also run a satellite messaging platform as a software as a service business, where we can send messages to any device on the satellite network. So you could be climbing Mount Everest and you can get your Iridium satellite phone out and send a tweet, or call international rescue and they'll come to your aid. And we that's right. And we help pull fishermen out of the water if they fall off their boats around the UK shores. We work with the RNLI to send them messages over the satellite network. So out of a lot of those learnings, we got really familiar with how to build stuff on Azure, and out of that we kind of got introduced to Orleans, and I've luckily had access to Orleans for about a year now, and I wrote a lot of the samples that shipped with the SDK, and wrote a lot of the documentation that shipped with the SDK as well. So I know a little bit about it, and I know the team behind Orleans fairly well. So kind of the Internet of Things it seems like quite a new thing. There's certainly a lot of hype around it. I remember back when I first started doing web programming and internet-based applications, classic ASP days, I was only ever dealing with a few clients, tens of customers, or maybe hundreds, or maybe 1,000 customers, but no more than that. But now we're starting to see demands on us as developers to provide systems that for ever-increasing numbers of devices. So with the Internet of Things, we're talking about thousands or hundreds of thousands or millions of things connecting and sending in telemetry data, and we're having to make some kind of sense of this and make some judgments. So this presents us as developers with some unique challenges. With the Internet of Things, we have hundreds of thousands of devices, which is far more than we're used to dealing with. We're seeing really high message throughput, so some of these systems have extremely high telemetry rates, and they can be throwing data out at a very high speed. And we have to react rapidly to changes in the environment. So this device that might be monitoring something like a wind farm or a power grid or something like this could be sending us some really important information, and we need to act on that quickly in order to save money or save the system or save lives, like we do with fishermen. We're also seeing some interesting ways in which these devices interoperate. So if you imagine a car may have a number of sensors on it for the engine speed and the fuel level and so on and so forth. Only by combining together readings from all of these different sensors do we really build up a picture of what's happening on the vehicle. We can't just take one sensor in isolation. They form a greater unit, and we need to consider a whole system rather than just an individual thing. And from a programming perspective, that's quite a different way of thinking about programming. We're used probably just to doing angle brackets over data, where we push data into a system, it comes back out again. It's quite vertical, it's got up and down. Whereas with these kind of scenarios, you can see far more cross-chat between the servers. Same's true for social networking and sites like Facebook and chat applications and stuff like that. There's far more cross-server communication than we're used to doing. So I don't know whether anyone recognises any of these challenges in their day-to-day job, or whether this is just me brainstorming, but this is allegedly what we're seeing in the field. The hardware landscape underneath us is changing as well. So when I first started programming with my Turbo Pascal 6, I had a single computer with a single CPU on it, and I wrote simple programs that run in a single thread and do one thing after another, and life was good and life was easy. But now we're seeing that Moore's law is only really being fulfilled by parallelization, and clock speeds aren't really going up. We're just getting more and more cores on the board. So it's fairly typical to see things like 8-core machines. You can certainly fire one of those up in the cloud, as Planky has just shown us. In fact, the maximum on a Windows server is currently 320, which looks like this in Task Manager, which is a really interesting, quite cool. It's not my machine, I wish it was. It's a really interesting picture. Each of these numbers represents a core, and you can see they're all white, which means they're all pretty much idle. So this machine isn't particularly busy. Apart from this core here, which is at 100%. So there's obviously some process running on this box, which isn't written in, it is exactly Task Manager, yeah. Who knows what it is? It probably is Task Manager. So it's not making use of multiple cores available to it. It's a single-threaded process that's currently being, could run faster if it was re-architected or had more CPU power available to it. So it just kind of illustrates that this is a hard problem, and we're really suffering from this as developers. So with developing for multiple cores, we found through some practical experience over the last few decades that this is hard, and concurrency problems are hard. And object orientation, the tool that we've been really using for the past decade, doesn't really work. And that things like shared state is a real problem for us. And we find that if we've got two processes trying to read the same variable at the same time, we can have corruption, or we have to introduce locking and synchronization code, and that's really complicated. And we as developers don't really want to have to do that. Anyone really enjoy doing multi-threading and concurrent programming? Anyone had to do any debugging of that? We've got one. This guy will solve all your problems at the next break. He's the pro. So we've really seen a move towards functional languages, or certainly a lot of people talking about them, in using things like F# with immutable state to try and solve these problems. And we're seeing things like software transactional memory and other crazy techniques to try and stop this concurrency thing happening. And this is even compounded further by the introduction of the cloud. So we've got multiple cores on a single machine, but with the cloud we have this, again, this huge horizontal scale out. So we saw I could go to hundreds of machines. We could be going to thousands of cores in the cloud. And this makes life even harder, because when you start to have lots and lots of pieces of hardware, failure becomes a fairly regular event. So when I first started programming, if my machine failed, if the disk stopped or the processor stopped working, I was far more concerned about my computer than I was about my crappy software. But that's really turned on its head now. And if a machine breaks in Azure, I don't care. I just fire up a new one. Machines are disposable. I don't care about hardware anymore. It's just a consumer kind of thing. So we have to build software that handles failure. And we found that this is hard, because building distributed systems in the first place is not easy. Traditional architectures tend to let us down. I'll look at why I think 3-tier architecture doesn't always suit us. And failure happens, and we have to deal with it. Failure can be a whole machine lost, or it can be the network getting congested and we start to see things run slowly, or it can be transactional or transitional kind of problems where we see a service in the cloud disappear for a few minutes and come back again, or one operation fails. And to quote one chap I heard recently, there's two kinds of people in the world: those who love cloud and those who've used cloud. And I think that's really compounded by the failure thing. And my personal experience is it doesn't always work all the time, and please put retry logic in your code to cope with that. So why do these traditional architectures fail? Well, let's just think about an Internet of Things scenario. We've got hundreds of thousands of devices out there, all reporting telemetry information back at a high rate. We would stand up some kind of web app, web API, probably running simple web, or something like this. Probably state rubbish, okay. ASP.NET VNext, is that the cool thing now? Right, cool. Or it could be something like Node.js. So they will probably make that stateless, because we want to have high scale, and we can't really scale with shared state, so we have stateless web servers. That's the thing we do these days. So we need to then store state somewhere, so we tend to put that in a relational database or some kind of database. And then we load the state up every time we need it. But that's a problem, because going and talking to a database, which could then be loading information off disk, is slow, and we introduce latency. That's not the main problem with relational databases. The main problem is is that they're a scalability limitation. So it's really hard to build a highly scalable system that deals with loads of throughput when it's all got to go through a single database. And okay, you can cluster or federate databases, but that tends to be problematic and lead to further problems. So we could go for another approach like CQRS or a NoSQL store with eventual consistency, and we can scale and shard and do all these great things. But then I've got an eventual consistency problem, and my data is either out of date or it's kind of partial, or I don't have the whole complete story. And when you're trying to make a really important decision about whether you should pull someone out of the sea or not, having out of date or incomplete information is not good enough. You need to have the latest information and all the information up to date and consistent. So although these definitely fit certain problems, I don't think they solve my problem for me today. But don't worry, all is not lost. For there is Microsoft Orleans, which will solve some of these problems for us. But what is Orleans? Did anyone watch the build session where Hoop, one chap, showed us how it all works? Well, I'll just do a quick kind of overview, and then we'll actually go into Visual Studio and have a look at how this stuff works. So Orleans is a framework for building distributed systems. A very clever set of people called the Extreme Computing Group in Microsoft Research have assembled this by looking at best practice and all the leading thought about how you build these distributed systems and solve a lot of these problems, and they've distilled it into a framework that we as developers can then use. It's designed out of the box to run in the cloud, specifically run in Microsoft Azure. In fact, it can also run out of the cloud, and you can run it on premises as well. And it is a .NET implementation of the actor model. Anyone familiar with the actor model? A few guys. The actor model was designed in the 70s by Carl Hewitt and is a mathematical concept for concurrent computing. Was inspired by particle physics, and so Richard could probably understand it, but I can't. And it talks about having lots of small little pieces that all talk to each other using asynchronous message passing. And we'll look at how that works in Orleans in a moment. So Orleans has been around within Microsoft for a few years now and been used internally to solve some hard problems. And was recently, at the build event, it was released and made available publicly on a public preview. So the main user of Orleans so far has been this guy, Master Chief, who is the main character in the Halo series. The Halo 4 cloud services, to all the online pieces to support that game, pretty much all run in Orleans. So all the data flowing from the Xboxes up into the cloud goes through the service bus and ends up in an Orleans cluster, a very large cluster. So whenever you shoot a weapon or shoot someone in the head or kill someone or whatever you do, that's all recorded inside Orleans. And then the second screen experiences and the web portal that allows you to go in and see your stats and how you performed, that's all Orleans. So going back to our scenario of building an Internet of Things system, how would Orleans work in that scenario? So let's go back to having a device or hundreds of thousands of devices. They would still send messages up to a web application. Now I've got web API there, but that in fact could be anything. I don't really care about the protocol. It could be AMQP or MQTT or service bus or whatever you want. We would still front Orleans with our own API, so we still build our own stateless service here to accept all these requests. We wouldn't normally expose Orleans directly over the internet. So when the request comes into this server, instead of going to a database, we're going to send the request over to the Orleans cluster that we're running in the cloud. And on each Orleans, or each machine that runs Orleans, we have a silo. Now, a silo is a container and is a huge memory space. And what Orleans does is when the request comes in, it creates something called a grain, which is this nice hexagon. And this grain kind of models the device. So you would typically have a grain for every device. And that grain would have some internal state, and it would know about that device. Maybe you're recording the name of the user on it or something like that. And that grain would then be able to make decisions about what should happen next and could respond back to the device and answer the question or record a piece of telemetry. Now, grains can talk to other grains, and in this case it's going across silos, but you don't really care in the grain code where the other grain is, you just send a message to it. In fact, you can have lots and lots of grains, and Orleans is designed to hold hundreds of thousands of grains in memory. So that the next time this device tries to connect to the system, Orleans holds onto the grain in memory and keeps it active for that device. And so next time, rather than having to activate it and load some state to serve an initial request, it keeps it hot in memory. So it's able to serve a request immediately, everything it needs to know is already in memory, the latency is very low, and so we've basically got a bit of a cache here, but you could see it as a programmable cache. The other job of a silo is to then deactivate grains when they're not needed. So when we stop sending requests into the grain, it'll deactivate, and we can go and store the state somewhere else, so that when the grain's asked for again, it can be reactivated back into memory. So that's how the system works. So how do we program a grain? What does it look like from a developer's perspective? Well, a grain is really just a C# class. It's a really small, simple, programmable entity. We're just writing C# here. It's single-threaded, it's asynchronous, and when I look at those three things, I realise why I like Orleans so much, because these three things describe Node.js, which is another big thing I enjoy. So a grain has internal state, so it has properties of the class or properties or member fields, and we're supposed to mutate them. We can change the values of those variables, and we can store those, and we keep that in memory. So mutable states is a good thing in Orleans. Grains can talk to other grains, and that's all via asynchronous message passing. Now, because grains are single-threaded, and we have one activation of our grain for each device that we're modeling, what happens if two messages come into the grain at the same time? Well, they get queued. So there's a message queuing facility on each grain called a mailbox. So when we start to throw more messages in than it can handle, the mailbox starts to grow. The one thing that's missing from grains, one thing we can't do, is we can't share state. So a grain cannot go and read or modify the properties or state of another grain directly. Everything has to happen over asynchronous message passing. So if you want to know something about the internal properties of another grain, you have to go and ask it, and it'll come back to you with the answer. There should be no singleton, there's no shared object that all grains should be modifying. That's really bad news. That's not how you build concurrent systems. We have to use message passing, and we have to use that technique to go and modify or read variables. So I think that's a fairly small thing to give away, given the benefits that we get and the guarantees we get of a nice programming environment of single-threaded, asynchronous, and message passing and all that. I think that's okay as a compromise. So grains live in silos. So what does a silo look like? It's a host of grains. It manages the grain's life cycle, so it is responsible for activating and deactivating grains. From the consumer's perspective, you don't care whether the grain is active or not. Orleans will just create the grain for you when you need it, and then deactivate it when it deems that you don't need it, using a garbage collection cycle. You are able to control that a little bit, but for the most part, you shouldn't need to. A silo is just a .NET DLL, and you can load the assembly yourself and fire it up from your own application programmatically, or it's available as a console app, or you can just bootstrap it into an Azure worker role. And silos are designed to work together. You can run them independently on their own, but they're designed to be clustered, and it'll use table storage as a high availability way of deciding which silos form the cluster and which is the primary node. Outside of Azure, you don't have to use table storage, but you lose some of the high availability there. You have to decide manually which is the primary node. So, in summary, programming in Orleans solves concurrency because we don't have any shared states, we don't have any problems. All the threading and stuff is gone. And we're back to simple programming as if it was a single CPU, although not in Turbo Pascal. It's simple. We can use C# who here knows C#? Probably most people, I expect. And so if you know C# and you know how to use async await, you can code grains and you'll know exactly what you're doing. It's a familiar environment. You can go and use your existing skills. You don't have to go and learn Erlang, and you don't have to be as clever as Richard or Mark to be able to build distributed systems. And it solves the low latency stuff because stuff is kept in memory. You don't have to go and ask a database for it. We can make really nice, fast systems that are concurrent, and we have all the up-to-date information, and we can make those important decisions. And finally, it's scalable and built for the cloud. So it handles failure scenarios, it understands when silos are down, and it'll balance out the grains accordingly. So there's some pretty smart stuff going on here, and some really clever thinking that's now available to us. So we're going to look at a demo. I'm going to build out some pieces in Orleans. And the scenario we're going to build is we're going to have a device which is going to measure the audio level in the room. And that's going to send messages over the Azure service bus, which we saw a little bit of earlier. And it's going to, we're going to have a worker process, which is going to dequeue the messages off the queue and not really do anything with them, but fire them straight into an Orleans silo. Now, the grains in the silo will receive the audio levels, and these grains will decide when there's been a peak in the audio level in the room. Now, to do that, they'll need some state, because they'll need to know what was the last level, what is the current level, has the level gone up above the threshold? If so, there's a peak, and it can tell us, it can report to us that that's happened. This bit doesn't exist yet, so we're going to create this live here now. Okay, any questions before we start? Do I feel lucky? I'm feeling lucky so far, but there's lots of moving parts here. Failure will happen. You have to embrace it. So here is my wonderful console application, which takes messages off a service bus queue like this, and when a message arrives, you handle the message, and we read the level of the audio off the... That's a very good point, isn't it? Let's just make sure that's... all right, yeah. Shut up. Right. Okay. Here is the service bus queue. Here we're handling the message, and here we're going to read the level from the message and then fire it into Orleans. Notice the horrible interlocked exchange I have to use because I'm in code that is parallel, and I don't have any guarantees around shared state. And I mean, should you have to do all that just to set a variable? It's ridiculous. And in here, we're going to send the messages into Orleans, and of course, I haven't done this piece yet. So the first thing let's try it out in its current state, so that we can see if it works. So let's fire this up. Nothing, that's good. And then I have does this work? Let's just get this going. It just demonstrates my wonderful WinRT development skills. This is telling us the current audio level in decibels. If I'm quiet. Goes down if I make a lot of noise. If you all clap. Look at that, we hit 40. So you can see, I'm reading these messages. You can see the number of messages I've got, the last level of the audio, and you can even see a little bar there to show you how loud it is. But of course, this app doesn't have any state, and it's designed to be... It died. Anyway. And so it's designed to be highly scalable and all the rest of it. So it's unable to make the decision as to whether there's a peak in the audio because it just sees values coming in and it hasn't got any context with which to make that decision. So let's first of all go and create a new project. Now, when I said that a grain is just a C# class, that was a lie. In fact, it's not. It's an interface and a class. So let's go and create the interface first. Anyone got a good name for a project? loudly, yeah. Loudly, and we'll call that interfaces, like that. So I've got the Orleans SDK installed, and so that gave me a couple extra Visual Studio templates. The first one I just used there. Let's get rid of stupid comments. Don't need that. And I've got an interface here which derives from iGrain. And here I can go and add in the methods I want to have on my grain. And I should be thinking of these not really as methods, but more as messages that I want to be able to send to my grain. So what message do I want to send to my grain? Yeah, the number of decibels. Yeah, someone's paying attention. And we know that grains are asynchronous, so what should the method return? SQL data reader. We could try that. So it should return a task, shouldn't it? And so we'll have a set level method, which takes a double, which will be the value of the loudness, and we'll call that level, like so. Interface done, and it even compiles. What are the chances? Let's change that from iGrain1 to iDevice grain. Sorry, a bit nicer. Right, let's now go and actually implement that project. So let's go to the grain collection here, and we'll call this loudly implementation.
My spelling's quite right there, isn't it?
Here we go. And here we would, first of all, need to add a reference. What should we add a reference to? The interfaces, yeah. We're all paying attention. You can't fall asleep. You must, let's get rid of all this stupid green text. And we'll inherit from iDevice grain like this. And we can just go and implement the members, can't we? There we go. So we've got a set level method on our grain now. So what should we probably do in set level? We should probably say how high is the level. So we also want some internal state, don't we? We want to store what the last level was. So let's have a double, which is the last value, like that. And then if the level here is greater than 35, and the last value was less or equal to 35, so we've detected a spike, it's gone over the threshold, then we'll report this out to our reporting system, console.writeline, to say it's loud in here. And we'll actually put the level in there as well. And then we should probably then set the internal state to be the last, to the value we've got, so we hold on to that. Right, level, yeah, good spot. Now why have I got a red squiggly underneath here? Because it wants a task as a return, but I'm not actually doing anything asynchronous. So one way I could solve this problem is to put the async keyword in there, which makes it go green. But if I'm not really doing anything asynchronous, it's a bit of an overhead having the async keyword there. So for convenience, Orleans gives us something called task done.done, and we can return that instead, which is just a completed task. It's just a way of making our code a bit more readable. So there we go. We've got a complete Orleans Internet of Things system now. All we need to do is test it. So let's build this. We need to go and plug it into my console application, which is over here. So the first thing to do is to get a reference to that grain. So we know there's a grain for every device. My method has got a variable for the device ID. So let's get something we can use to talk to that grain with. Before we do that, we need to go and add a reference to one of the projects we just created. Which project do you think we should add a reference to? The interfaces. Good. Very good. Because we're not running the grain code ourselves. Orleans is going to run that, and we just want to talk to Orleans and tell it what to do. So So we don't need a reference to the implementation. Instead, we just have a reference to the interfaces. And when I compiled the interfaces project, some magic happened, and it made some code for us. And we've got a device grain factory here. And that's got a method in it called getGrain. And this we can use, it's a bit like a proxy for SOAP. It's going to give us back something that implements our iDevice grain, then we can use that to then send messages through to the grain. And this has two ways of referring to a grain, either by a GUID or by a long. But we have a problem because our device is a string. So any ideas what to do? Hash it. Well, yeah, that's what I used to do. So you can, if you do an MD5 hash, that's the same number of bytes as a GUID. But there's a nice coincidence. But in fact, the Orleans team solved this before they released it. And if we go to the interface project, we can add an attribute saying extended primary key, like that. We rebuild. And now we can supply either the long or the GUID, but we can also supply an extra string as well. So let's just go call everything grain 0, and that's then augmented by a secondary primary key, a bit like a joined key in a SQL table, which will be our device. So we can still use a string to refer to a grain, we just have to do that extra step to do that. And that's going to give us a reference back to our grain. It hasn't actually gone and contacted Orleans at this point. It's just giving us the means to do so. And then this grain should have what method on it? Set level. So we set level. We've got the value here being passed into this method, which is level. And this is asynchronous, so what should we be doing? Await. But in fact, it's just returns a task, so I can just do return like that. And that should make all the red stuff go away. And it should all come. It's not referenced. I need to go and add a reference to Orleans from my console app. Here we go. So we should be all good to go. When I compile it, what happens is that the grain implementation project has a post-compilation script which goes and copies all the assemblies it needs over to a local silo I've got on my machine, and so I don't have to really do anything special other than just go and run Orleans. Question?
Serious question, honestly.
Yeah.
With the getGrain, the two keys,
Yeah.
the table storage, would that translate to a partition key and a row key? Or
That would be nice, wouldn't it?
Yeah.
Sadly, at the moment, it's not going to store any grain state in table storage. I'm going to do that in a little while, but unfortunately, using that dual key technique, you can't go and use automatic storage. So maybe in the future, but at the moment, no. Yeah. I'm just trying to think if there's anything else I need to do. I don't think so. So let's go into Microsoft SDK, CD SDK, and then start the local silo, which takes a few seconds to fire up. It's all just .NET code. It's written in C#, and I have no idea what any of this means, but it looks really cool. Looks like you're hacking the matrix. There we go. So we've got the green thing. The primary node has started. At this point, we can go and fire up my console application, which will be in the blue. Does that come across as blue? Yeah, roughly. And now, let's try and fire this wonderful piece of code up again. We're seeing that same old console application, but we want to see Orleans say getting loud. And it doesn't work. Something's gone wrong. What's gone wrong? Yeah, I think so. Oh, I know what I've done. I'll tell you what I've done. Stupid rookie mistake. Just get rid of that for a moment. What I haven't done is initialize Orleans in the client, which is a really daft thing to do. So this will be a good learning point for us all, in that in the program here, is that how does this grain know where Orleans is? Well, it doesn't. You have to tell it. And you do it. It's even got a to-do here, hasn't it? I should read my own code. Orleans client, let's just get that, has an initialize. And what that's going to do is you can pass in some XML or an XML file name, but I've already added a configuration file which just tells it where the local Orleans silo is, localhost port 30,000. So now it knows where to go and find Orleans. So let's just do the sequence again. First you start the silo, wait for that to start up, and we get the green confirmation. There we go. Now we'll start my wonderful program. Then we'll start this all running. My amplitude sensor, that's all working. Hey, it's loud in here. There we go. Yeah, so it works. It's amazing. Right, so let's just cancel that. We'll get rid of that. And how are we doing for time? Got more time for more stuff?
Another 10 minutes?
10 minutes, so we'll rush through a couple more features, okay. So Mark asked about table storage a moment ago. So when I shut down Orleans there, my grain disappeared and its internal state will never be seen again. So what would be nice is to be able to save that state somewhere so that when my grain becomes reactivated in the future, it can go and load that state. So there's a couple of ways you can do that. You can go and override a method here, which I'll show you in the grain implementation. I can go and override activate async. So this is a method that's run when your grain is started before any methods on it will be called. And this gives you the opportunity to hook into SQL Server, RavenDB, or whatever you want to do to go and load some state from a database and initialize your grain with the information it needs. How do you know what grain you are, though? So that's an interesting question. So fortunately, there is a way of discovering your ID. So there's a get primary key long or GUID, and because we're also using an extended key, we can, so this method will return the long, which, because we're using two keys in this scenario, is the primary key, and there's this secondary key, which is the string, so we'll use that as our ID, and then we can use out ID, and then we can do a console.writeLine and write something like activated grain. And then if I won't bother running it again, but then you'll see when the grain activates, you'll see it write out that it got activated, and then you'll only see that once, and then you'll see all the other messages underneath it because it's kept activated in memory. There's another method, so you can override deactivate, so you can get called when you're about to be garbage collected. If you just stop the silo, you won't get notified at all. So you still need to save state as you go if there's some important state that's been changed in your application, because you never know when failure may happen. But going and reading and writing to our own storage system is a bit too much hard work. So there's another way you can do this. So Orleans provides us with an automatic persistence infrastructure. So we can specify an interface which we can use to say what kind of state we want to store. So we'll call it my state, and that implements iGrain state. It's gone green, that's a good sign. And here we just put in what we want to store. So in this scenario we're doing the level, aren't we? So we could have something like the maximum, the current level. Should be like that. Which is great. Now all we have to do to use this state provider is to change grain base, so it does that. And then we specify which store we want to use to store the information in. Provider name is Azure store, and I'll see how this works in a second. And then we can get rid of this internal member variable because we no longer want to store that. Instead, we have a new property called this state, and that's got the level on it. So we start using that instead. Simple enough. And then when we want to persist that state, we add in one line here to say this dot state dot write state async, and we should probably await that, and we should probably do async there, and we should probably just do that. So now we have a grain which is now persistent, and Orleans will go and activate that grain for us, load the state, set that state property for us, and that'll be initialized, ready for us to start using, and we just use it like this. And when it changes in a meaningful way for us that we want to make sure gets saved to the backing store, then we just do write state async. How does this work? How does it end up somewhere? Well, if we go and have a look at the Orleans configuration XML file, which is sat next to the silo, it's got some storage providers here. And we can see there's a provider called Azure Store, which is the one I used. And that's going to go and use something called the Azure Table Storage Provider in Orleans, which is basically just going to write out our state to Azure Table Storage. Fantastic. We can swap that out for other providers. I've got a blob storage provider, which stores it as JSON. You can go and store it in a SQL database. Some other guy today showed me he's written one for RavenDB. So we completely separated out the grain code from the storage mechanism. Those two parts are decoupled, so you can swap them out and use whatever you want, which is quite a nice feature. One final thing, and then we've pretty much done all there is in Orleans, is perhaps our grain wants to, let's just remove the storage stuff for now, because we know that doesn't work with the extended key. Perhaps we want to set up some logic in our grain so that every few seconds it goes and notifies some other system about the current value of this device we're monitoring. Perhaps if there's an error condition, we want to go and regularly go and say there's a problem over here, and if it's still the problem, we can go and do that again and again and again. So as we have it at the moment, we can't really do that because a grain just responds to incoming requests. You can't really put in a traditional .NET timer here because you should at all costs avoid trying to run code in other threads. You have to use the Orleans thread pool, and so you have to use the Orleans way of doing things. Parallel task library, definitely no. Everything should be managed in the Orleans thread pool. So how do we set up a timer? Let's just go do lots of Control Zs here. There we are. Get a few more. Great. So when we activate, we could do this register timer, and this is going to take a callback function that it's going to call. We'll just call timer called or something like that. We can pass in some state. Can't be bothered. We can say how many seconds we want until the timer gets first called, and we'll say 2 seconds, and then what reoccurrence do we want that thing called? This is just exactly the same as the standard .NET timer. We'll have that call every 2 seconds again, and then we just need to implement timer called, and that's going to take some kind of argument we don't really care about, and that's going to report to our reporting system that what the latest value is or something like that. Last value, isn't it? So let's just see. Oh, it needs to return task done, doesn't it? compiles. Let me just make sure I do a rebuild on that.
Would a timer like that stop the grain from being cooling down?
No, it wouldn't do. I don't know actually. I'd have to get back to you on that one. There's two kinds of timers. There's a timer which runs while the grain's active, which is one of these, and there's a timer, a reminder you can get called, which will go and activate a grain to respond to that reminder. So I think a timer will only run during the activation of that grain. So let's start the local silo again. Wait for that to start. Come on. Let's fire up this app. Let's start this again. And we should start to see some data come in. We should on here. We're seeing the timer running and telling us what the latest value is. So the timer code works. Fantastic. That is the end of my demo. Definitely got loud then, so thank you. So just to sum up, we've done that. This is going to work. Yeah, in summary, so what did we learn? Orleans makes programming a cluster of machines feel like programming a single machine again. It takes us back to when we first started programming and life was simple and single-threaded and we didn't have concurrency. So I think it's a huge win there. We can use our existing C# skills and we can carry on and build hugely distributed apps and can handle enormous scale and lots of throughput and all the rest of it without worrying about the complexity or being have PhDs in distributed systems. It's also great for building systems that require high availability or high throughput or low latency or has a lot of concurrency. So if your problem looks like one of those, that's great. If you're building a blogging engine, Orleans probably isn't going to be for you. It's not general purpose, it is niche, and we're starting to see these kind of areas be a really good fit. Go and download it from here, or follow me on Twitter if you want to see what I'm up to and get some updates on what's happening in Orleans. Thank you.